There you go.
Hello, everybody, and welcome to Serbia and the city of Niš. We are in the Niš Fortress, which is a Roman, then Ottoman Turkish fortress. And this location behind me is the Serbian Hydrometeorological Division's governmental weather station. You see a lot of weather instruments behind me in the field. And we are here to see a balloon launch by this robotic balloon launching machine right here, this green shipping container. So that balloon will come out at the top of, not the top of the hour, but it will come out at 15 minutes past this hour. So in about 15 minutes, we're going to see a weather balloon launch. So we also have with us Steve Randall. Steve, do you want to say hi?
Hi, guys. It'll be interesting. I'll be really interested to see this.
Yeah, Steve is helping out. He's taking care of a lot of the behind-the-scenes video switching stuff. And Steve and I have known each other for a long time through our amateur ballooning, and kept in touch from early projects. So one of the things we're going to do after this balloon launches is to take a tour of these weather instruments here in the yard. And this is an interesting collection of old and new instrumentation by the Serbian Weather Department. So feel free to drop into chat and say hello. After the balloon launch, we're going to go ahead and actually look up close at all the weather instruments. The weather instruments out here in this field. I'm very grateful to the staff here at the meteorological station. They actually gave me a full tour of all their equipment and even inside the robotic weather balloon launcher. They and I had a great time. It's very rare that weather balloon people cross paths randomly, and we had a lot of fun. I was quite interested to hear the history of their weather program. They have maintained this connection to the historic instruments that are all manual and read by hand until the present day, so that there's always a backup in case the electronics fails or the power fails. Later,
is that a ladder behind you, Dan, for climbing up to the anemometer?
Yes, indeed. Yeah, you see right here is a ladder on the mast. That is an old-fashioned anemometer, again, in that old generation, that actually has a lot more mechanical stuff that needs to be maintained at the top and troubleshooted occasionally than a modern anemometer system would. It actually uses pneumatic sensing, mechanical rods, and actually one section of it is hydraulic to sort of register the average gust level. But after the balloon launch, we're going to look at the manuals and the data sheets from these cool old instrumentation like that one. And we're going to stream for probably about an hour and a half here, hour and 15 minutes. So we may have little gaps in chatting, but feel free to drop a note and we will keep you updated here as to what's going on. The balloon is expected to pop up in about 10 minutes. Steve, would you go to the, if you're still there, Steve, would you go into the captions tab and click that 15 minutes title?
15 minutes. Okay, yeah.
There we go. Perfect. That's one of the things I like about the streaming platform is really easy to throw stuff up on the screen like that.
Yeah, it's like a little studio set up on the web.
Yeah, it's honestly it's just right. There's not enough to be confusing and overbearing, but as we see a beautiful view here in the evening at Niš, Serbia, we're looking out, blocked by the trees, but we're right at the edge of this Ottoman Turkish fortress, right at where you see the trees in the background beyond the weather station, is the giant stone wall that would have been behind the moat of the fortress. It's fairly well preserved here. And at some point on the stream, we'll take a look at this, the view from this center of this valley that is surrounded by beautiful mountains here in Niš. This is actually I think a national park, national monument here, and it's about 80 hectares in area, this fortress. I'm not sure what that is in acres, but maybe about 50 acres, just estimating it. But it's open to the public 24 hours, which is nice, and a lot of the big giant gates are preserved. And this weather station is placed here. It's a nice raised, basically plateau right in the middle of the city, and that allows them to get, with some trees around here, it allows them to avoid the problems of like thermals and shading in the city that would normally be an issue for accurate weather sensing. We'll take a look around here again. Let me loosen my tripod just a little bit. So we see that the white building there is the actual weather office, and right behind that is the robotic weather sonde launching device here. This is actually a product by Meteomodem, a company that makes radiosondes themselves. And this device is called a Robotsonde. What it actually does is it takes a prepared set of balloons and you program it to inflate and release the balloons on a schedule. And you will time these 2 times a day is the bare minimum for world meteorological stations. And just checking something. Generally, they're launched at a minimum of twice a day at midnight Universal Time and 12 p.m. Universal Time. This particular station adds supplemental launches to get more data 6 hours after each of the standard soundings. So this site does 4 balloons per day at midnight, 6 a.m., 12 p.m., 6 p.m., which is really nice for those of us who are fans of watching balloon launches. You get your choice of times. Here in the local time zone, which is UTC +2, that puts us right now at just after 7 p.m., which is very nice. The sun has just set. Is it 7 p.m.? Yeah, 7 p.m. The sun has just set, and it's getting a little chilly. But the other time of day that this will happen in this time zone is about 1 in the afternoon. So that's nice. Nice and easy one. Last weekend I did a broadcast of this launch, the 1 p.m. launch, which was nice, but it's pretty hot out here and a lot of tourists wandering by. Feels a little less exposed and less out of place standing here in the evening. So this device generally takes about 15 minutes to fill the balloon, and I think the device starts an external warning siren or beeper and flashing light to warn people around and who might go inside that it is in process of filling. And that light is, let's see here, it is right here, little orange light behind this little antenna, and that will start flashing, and we will hear a faint beeping, sort of like a digital watch, when the helium actually starts flowing into the balloon. And these balloons are standard weather balloons of the type that amateurs use frequently. They are latex weather balloons, spherical, and the particular specification that this launching site uses are 500-gram mass balloons made by the manufacturer Totex from Japan. These balloons are expected to rise up to about 30 kilometers before they burst, reading data every 1 second back to the ground. And you'll see, in fact, that data is transmitted via 402 megahertz radio data modem, and it is received on the antenna that is right here, the antenna that's actually blocking the orange light. And that is, you can tell that's a UHF antenna, because it's about 3/4 of a meter long there. Hello, Peru Mapper. Welcome to See a Balloon. You're on stream with chat. So we have Steve back at the in the UK, and I'm Dan Bowen, Balloon Side Dan, out here in the field, and we're waiting for a balloon launch to start out here in Niš, Serbia. This is a Serbian government weather station where they take readings of all of the different weather properties multiple times per day, continuously for some, and they launch weather balloons here, also known as Radiosonde. They do those 4 times per day generally. So feel free to drop into chat and say hi. Steve, let's see. I don't know if we can get our. Let me see if I can change my name on here and have us be separate names.
I'll leave you to do that.
Yeah, very carefully. Because if we get Dave and Tom on board here, it will be confusing.
Did you say helium? They're using helium for the balloons, Dan, not hydrogen.
Stand by. Let's just see. The names are not showing up. That's okay. Yeah, they are indeed. Go ahead and disable that banner, Steve. About 15 minutes after the hour, it appears to be delayed. We should have heard the beeping noise and such by this point. Thanks. And feel free to put up another one that looks relevant. So the Peru Mapper asks, what is the apex height of the balloon? That's a good question. And generally, these balloons that they fly will go up to about 30 kilometers. How many feet is that, Steve? Do you know?
That'll be close to about 100,000 feet. 30 kilometers, yeah.
Is that about 3 times what airliners fly?
Yeah. I think it's just a shade under 100,000 feet, 30 kilometers.
Yeah, that makes sense.
Yeah.
And we don't have a live mapping tracker for these here right now, though amateurs have developed receiver systems that can decode government radiosonde transmitters. And actually, since the transmitters broadcast their GPS info all the time, every second or so, amateurs have figured out how to go and collect them for reuse as amateur balloon transmitters, which is really cool. Because normally, Weather Service balloons and their electronics are just left to be found or not be found out in the environment. It's determined that it's so important to get weather data that there's some sort of acceptable littering that goes on, but they are labeled to explain to people that they aren't just trash, that these are safe to pick up and dispose of, or to return to the National Weather Offices. Hey, it's Uncle Russell, Adirondacks for me. Come on in. It's okay. The balloon is late as well. It is hopefully going to be launching any time now. I'm actually going to check on the launch time. Oh, hey, it's going to launch. It wasn't beeping. Here we go. It's actually launching. You see the roof is retracting and it's sliding off to the right here, right here. And the balloon, there's the weather balloon. Beautiful sunny night. Look at that. You can see the package, the payload below it, swinging around. See, swinging left to right and rotating. And it actually extends downward as it flies. As it came out of the launch, by the way, the balloon is right here as we see it flying. This little white dot. It's already climbing probably up to 1,000 feet at this point. They generally climb at about 1,000 feet per minute as it ascends continuously, although it may pick up speed over time during the flight. Is that about 4 to 5 meters per second there, Steve? We have Steve Randall in the UK. We're watching the weather balloon that was just released from the robotic sonde. I think I've lost it. Yeah, it's gotten too small to see. But that was great. It didn't do the warning beep, so it kind of caught me off guard. But as we'll see, you can see this white area here is a cylinder that the balloon actually is stored in during its inflation. It lays in a tray, a carousel, a round carousel of 12 balloons that they have carefully laid out in a zigzag and connected to a disposable nozzle for each balloon. And when the time comes for a sounding, which is a balloon launch, the carousel will rotate a balloon and a little styrofoam electronics box attached to the balloon, rotate it under this cylinder, and the helium will start flowing into the disposable nozzle with a one-way valve that is in the end of the balloon. And the balloon will slowly fill and stand up until it reaches the proper amount of gas to lift the payload at the speed they want. And when it does that, it stops the helium flow and then opens up the roof, where we saw that this part of the roof, sort of a square on the top, slowly slides back this way, exposing the open cylinder. And then the mechanism will let go of that disposable nozzle and the balloon lifts out. And between the balloon and the electronics box is a little cylinder where the string is wrapped in a very special way around this cylinder so that the string doesn't come off right away. And that's important because this is a very long string. To get good weather data, your sensors on the electronics that hang below the balloon have to be well out of the sort of the turbulent air that is caused behind or below the balloon as it's going up. So it's not buffeted and there's no temperature change due to the sun heating the balloon. That warmer air doesn't contact the temperature sensors on the actual payload that comes out of here. However, you can't launch a balloon with a long string on it from a hole like this. And that's because there's almost always wind blowing. Hey, Steve, thank you for taking care of chat. There's almost always wind blowing. And what would happen is the balloon comes out slowly. And as that gets into the wind, the balloon starts drifting downwind. And if it had a long string going back into this hole here, it would drag that box up out and bang the box down here until the balloon climbed high enough because the wind was drawing it across. See, it is a little windy here tonight. Probably can't tell by the resolution of the screen, but what the device is that prevents this catastrophic crashing basically on launch is called a de-reeler, or sometimes known as an unwinder. This device again, has the string specially wrapped around it in such a way that the string very slowly unwinds when it's hung with a weight on it. And it takes probably about 30 seconds to get all of the string unwound. And I think it may be, Steve, you might know this, how much string is on a typical balloon? Is that about 50 meters, 100 feet or something like that?
I don't know for a weather balloon. We typically use 10, 15 meters on amateur equipment, but it is longer than that, and it's a very long string that they use.
They have a precise length that they need. I can't remember what it is, but it's long. Like I say, it's somewhere around 50 meters or something. So that's a lot of string to pay out, and so that's what solves that problem. It's a very elegant solution, and that's used by radiosondes worldwide, and it allows one person or one robot to launch a balloon alone. Whereas if you had a long string, like 50-foot string between balloon and the box, it really requires two people to do that, so that the one holding the box hangs onto it, and the one letting go, the person lets go of the balloon, and the person has to hold the box and make sure that the balloon lifts up over the top of the box before they let go. And that requires field space and coordination with people, and it's a pain in the butt. As amateurs, we've done that a lot because I don't think most of us knew about derailers or unwinders for many years. Steve, do you want to say something about how you've sort of reverse engineered those to be used for amateur balloons?
Well, I've built some of the triangular shaped ones for a couple of flights they've done recently, just because it's made the launching process so much easier. They're you just literally hold the payload from the neck of the balloon, and it just dangles down a couple of feet underneath the balloon, and then let go. And as it goes up, the payload comes down. I mean the D-reel is really a very useful for light payloads. I think when you get to quite a heavy payload, it might become a lot more difficult to do. And I have seen some fairly hefty mechanical ones for larger payloads. Yeah, if you're launching something a few hundred grams, then an ordinary D-reeler is just great. You know, it makes it so much easier.
That's a good point. The mass of the payload would affect that, because in my use of derailers for radiosondes, oh, hey, we'll get back to that. We got a couple questions from stream here. So Peru Mapper says, what's the real name of weather balloon, since not always used for weather? Good question. I mean, most of the names are weather related. Like there's some call it a sounding balloon, which is a weather measurement. The other use would just be a high altitude balloon or latex balloon. Do you know any other common names, Steve?
Meteorological balloon is another weather related one. Just a large latex balloon. I mean that's really what they are. They're just equivalent to a party balloon, but a lot bigger. You know?
Yeah. Hold on 1 second. Can we talk about the derailer? I just lost a nut out of this tripod.
Okay.
I got it. All right. And Adirondacks for me says, wish I had the worldwide patent for that underwinder. Yeah. There are a lot of these balloons that go up with unwinders every day. Thousands. In the U.S. alone, I think there's 400 per day.
Right.
At least 400 per day if they're twice. I think there's 100 or 200 sites in the U.S. Do you know worldwide, Steve? How many you might guess sites?
Well, certainly thousands, I should think.
Yeah.
In thousands, yeah.
So yeah, weather balloons are a pretty high volume business as far as scientific devices go. Pull this back down here.
It must be a reasonably big market for radiosonde and latex balloon producers,
Yeah, it's thankfully, and that makes the radiosondes fairly cheap and the balloons relatively cheap. They're still kind of expensive for amateurs. A balloon, 500-gram balloon. Steve, you sell these balloons. You resell them, don't you?
Yeah.
What price do you usually put on like a 500-gram?
So in Europe, they're about £25 or a bit more in euros. I guess in the US they're probably a little bit cheaper, but like I was saying, it's a pound to dollar thing, and most things are priced in dollars. In Europe, you're having to pay import duty and things on them, so that pushes the price up. But they're not astronomical. I mean, the cost of helium now is in the sort of private market is coming up to the cost of the balloon.
Oh, right. Yeah. It's a lot of the world weather services do use hydrogen for their balloons. The U.S. I think now does, and many have for years. And it's easy to be done safely if you follow careful procedures, but it's also possible to have accidents with hydrogen when filling balloons, and that's not, it has happened in the past. This site actually uses helium because they have had an accident in the past, and the government wanted to be extra careful for the future to not put any technicians' lives at risk or injury potential to keep that low. The hydrogen is a lot cheaper than helium, though, so that's the main driver for weather agencies that might want to use that. Like, I do believe the U.S. weather sites all use hydrogen now. So we've got a question in chat again. So, not sure that everybody knows that there's a limited supply of helium. That's a good point. There is indeed a finite amount of helium on planet Earth, and it's not something that we know, it's not something that we have the capability to create. It is scientifically possible to create helium, but it requires fusion. There's no chemical reaction that can do it. And the only bulk factory that we have for producing helium is our local star, the sun. If someday we get fusion reactors going fast and productively, we might produce helium. But for now, helium comes out of gas wells, just like any natural gas, methane, etc. And in fact, it is not produced the same way methane is, natural gas, because that comes from the hydrocarbons, the former biomatter of the ancient Earth, algae and bacteria layers underground. But helium actually comes solely from minerals like uranium decay.
Yeah.
Because the decay of uranium, when you say there's radiation coming out of uranium, actually little helium nuclei or parts of helium nuclei that are zipping out of uranium at high speeds. And I forget the details. Is that like a proton? Do you remember, Steve, what the particle is?
No, I know what you mean though. It's
Like a proton.
It's the nucleus of a helium, which then just acquires an electron somewhere, I think, and becomes free helium. And I'm not sure that they actually mine it though. Do they mine it independently of natural gas or
not? No, that was never done until recently. Until industries realized that supplies were running low. In modern civilization's history, helium has been a waste gas for natural gas wells, and only in the conditions where there is uranium in a sealed pocket of underground rock, where those little atoms of helium can build up. And by build up, it takes millions of years, or at least hundreds of thousands of years, for enough of these to add up to a quantity that we could put in a balloon. And it's lighter than methane, just like it's lighter than air. So it collects at the top of these underground sealed chambers that hold the natural gas, which has come from the decay of old biomatter. And in the 19-teens and 1920s was when helium was first identified, but was when helium was first understood to begin these natural gas wells. And before that, in the late 1800s and the early 1900s, natural gas wells viewed this as just a waste, a perplexing gas that wouldn't burn and wasn't good for anything, and had significant quantities of it at the beginning of every new gas well they tapped. Wind gas was the name they gave it, and what they would do to be able to get to the useful gas was they would just leave the gas well open, spewing helium for weeks at a time to get rid of it so they could get to their gas product they wanted, which is a terrible loss for civilization because it is far more rare than natural gas. And things like natural gas and hydrocarbons, we can actually create those through chemical processes, but we cannot create helium. And recently, Steve, as you had said, there's not been mining, but recently there have been efforts to explore for the presence specifically of helium, independent of whether it's present with commercial quantities of methane or not. And that's because we're running out, and there's pressure economically now to try and find helium in ways that are expensive, but are better than not having helium at all. So let me get a drink here. So we've got a question here. So this setup is fenced off in a public park. Great field trip for students. Yeah, absolutely. Indeed, it is fenced off in a public park. And what a good segue. Let's go take a look at these before the light has waned. I'll give you a tour and tell you about them. Steve has some actual brochures and manuals that I've found for these instruments. We'll look at the new ones first, and then we'll take a look individually at each of the antique classic instruments that they use here for backups. Still read every day on the hour as backups, and they maintain their precision adequate for standard weather observations still in a style that was first designed in the early to mid 20th century. So let's take a look here. So we see over here on the left is the old anemometer building. This is the classic anemometer, which we'll talk about in a minute. And up here in the middle, you see there's a tower there in the middle, and that has the modern wind sensors, which are the anemometer and the wind vane direction indicator. I'll try and get in front of the wind so it's not so loud for you guys. So the red and white pole is the modern sensor. And as we go by here, most of these instruments are classic, old devices. So basically the modern equipment is very few and far between. They're mostly all on that big tower. So let's actually start looking at some of the older equipment here, Steve. Do you want to throw up a half screen of the heliograph, the solar instrument? So this instrument here is a very old style recording solar heliograph. And you can see there's a glass ball on top of this pole. It's hard to see in the film. I wish I could zoom in better. There we go. Let's do half screen. You do that. So let's go ahead and turn off chat for a moment. Here, I can do that, Steve, while you're getting the pictures up. So we can see that there is a glass ball surrounded by two little forks here. Let's see if we can see. Two little forks. And on these little horns, there's a strip, a black strip, that the sun shines through this black ball here and focuses onto the little strip behind it, and it burns the ink off that little metal strip. And what it ends up doing is it records the track of the sun across the sky for reference to their meteorological readings. And all these, there we go, beautiful. Thank you, Steve. This is made by the German manufacturer Fuess, Fuess, and this is the exact same one that we see on top of the pole here behind me. And you can see that the markings on the little black ruler behind the glass ball there. And I think this will keep a reading for a long time. Do you see anything in the manual there, Steve, about how, if we scroll, how it might, if it's used, if it has to be replaced frequently, or if it's left in there for long periods of time to get multiple tracks? So we have a beautiful manual for these things, which I'll put up links to these manuals later in the descriptions after the webcast. So there we see sun's rays are focused on a card, and 3 overlapping pairs of grooves are provided in the bowl to take different cards around the year. So, well, let's see if we can scroll up and we see any, actually scroll so we see down farther in the page. Beautiful instrument. So yeah, keep going. I really appreciate you running the documents, Steve. Oh wait, go back up to the specs. Changing of cards, there we go. It says daily. So it is just going to produce one track across that black strip daily to be recorded and kept for records. So let's move on to another. You swap me over, Steve. There we go. Awesome. So we'll move on to another instrument. I'm going to the instruments that are farther away from the light as it gets darker here. You can see this sort of tin can looking thing on the ground. And this is actually a rain gauge that is clockwork operated. It actually has a little paper chart recorder in it and a little mechanical counter. And the little wind-up clock actually rotates the drum with a little ink needle that steps up every time a little bit of water fills a cup and tips over. And we'll look at the manual for that one later. We can see these are the modern instruments. Before we go on, though, let's go back to this strange one behind these two. We've looked at the solar heliograph and the rain gauge. But there's this one here that, you see, there's these little wires between poles. Get a little closer to that. And this one, by the way, the staff of this office so generously gave me a tour of all the facility and explained what all of these wonderful, beautiful instruments do, that I could tell sort of what they were meant to do, but how they worked was, a puzzle for such mechanical systems. So this one, this little white wire, there's a wire here, and also between the poles here and here. And what this does is it's used to, let's see if I can get in the shot here. It's used to measure icing. When there's ice storms, the ice actually collects on those rods, and every hour the technician will come out and measure how thick that ice is. And that data is used by power companies to tell throughout the year and then from climate maximums how much icing a particular region gets. So they know how heavy the ice load might be on their power lines. That allows them to specify the type of strength of power wires from between power poles needed to survive winters in that region. Isn't that interesting? It's such a simple little device. Now this, we see here, there's standing in bushes. Here there's a, just standing like this on camera, this little bottle with a red funnel on the top. This is one that I had no guesses for, other than I knew it was a rain gauge of some sort, but there's like 3 or 4 other rain gauges out here already. And I was like, why would you have a bottle? It actually is it's a collection for atmospheric precipitation for radioactive particles. It actually fills with rainwater or snow, and they just let it evaporate out, and it leaves dust and particles behind over time. And this is an academic instrument, collection experiment from China, from a Chinese academic institution, where they are interested in collecting what kind of radioactive particles are present across the world, both naturally and man-made. Can tell us a lot of information. And this site actually hosts 3 radioactive particle collectors. Again, just, I had no idea that would be something here at a weather site. So we'll see the other 2 radioactive collectors. In fact, you can already hear one of them. Let's take a look. You see this little white box with the roof on it? That is making the roaring noise. It's actually a weather product from Ocala, Florida, or Olalla, Florida. I don't know the brand, but it is pulling air through filters at a very high speed. And that is meant to collect the actual dust in the atmosphere, very fine dust particles, onto filter cartridges, just like N95 masks, but for science. And it sucks it through all day long, and once a day, they will go in and pull the cartridge out, seal it up for analysis later, to make the count of what kind of radioactive materials and what the particle count and strength is from those materials. By the way, at the top of the hour, we expect the data from that balloon to come back to us on the web. The Serbian Hydrometeorological Division here wonderfully publishes the data results from their balloon flights as soon as the flight is over, automatically on the website. And Steve is going to pull that up for us when we get to that point in time. Thanks for chat, Steve. And have we gotten any messages in the last little bit there? So we see here, if we've missed your message, feel free to just drop it in there again. We've been zoomed in and I can't see the messages all the time. Let's see. So this little house here, which in Serbian, the term they use is a bee house, like a beehive, like a beekeeping house. It is what's called a Stevenson screen. And in my last video here, I incorrectly identified it as being having a fan that blows air up and out those slots. It is for having air move through it, but what it doesn't have a fan. It just uses natural wind and air convection. And the reason why, this has a reflective roof on it and has gaps right below the roof. There we go. Thank you, Steve. This is meant to shelter instruments that would be negatively affected by direct sunlight, like a thermometer. Like outside, if you've ever had a thermometer in the sunlight, you know it will read much higher than it would have if it was in the shade. So this provides shade to measure the real air temperature. And they have some beautiful instruments, just straight up glass thermometers and glass hygrometers in there. That they read manually. They open up those doors, you see, open up the front doors, climb up those little stairs, and note the reading on the super fine little precision lines on there. We can't see in those tonight directly, but later on, Steve will bring up the actual manuals that show us pictures of those super beautiful glass thermometers and hygrometers. And I've got to tell you, it's way more complicated than a thermometer and a humidity sensor. They have some pretty neat mechanical ways of measuring maximums and minimums with glass thermometers without... Anyway, we'll come back to that when it's... I want to show you everything before it gets too dark here. So we see up here is there's the old style anemometer, which is, again, that's the mechanical anemometer. We will take a look inside of that. There's a lot of mechanical bits and pieces inside this little house that allows this thing to operate, to collect data, and to convert motion and pressure to actual chart information. You can see this little vane that I can't do it backwards, but the little tail and the nose there. There we go. Thank you, Steve. You can see that horizontal bar with the vane on the left. It actually takes in air from the tip, from that little nose. It's a pitot tube. I think there's at least a port on the front and maybe a static port on the side to measure ram air pressure. So yeah, you see, it's not simple. There's even an oil jug in there that records things. We'll come back to this in a little while when it gets darker. Thank you, Steve. So we see here another little Stevenson screen house, and inside this one is a chart recording humidity sensor, like the... Sorry, my aiming is bad here on the phone. This actually records humidity, whereas the other Stevenson screen device that we saw over here, that just has live thermometers and hygrometers. Hygrometers measure humidity. But this one has a little paper cylinder and a little needle that goes up and down, which is totally mechanical. I believe wound with a key, a clockwork mechanism and spring that keeps the dial turning in there. And that one, we'll look again at the manual for that, but maybe Steve can bring up at least the picture. To sense humidity, back in the old days, they used hairs from humans or horses that actually stretch or contract based on the humidity. Like when things get damp, they relax and extend and stretch in length. There you go. There's a nice little picture. Hair hydrograph. Hair hydrograph. Look at that. There are, I believe, 5 bundles of human hair or horse hair that are all put into a little row that they call the hair harp. You ever think you would hear the word hair harp? But we'll look into the details of that a little later. There's one of the technicians doing the hourly checks on these instruments. He's going to make sure the data is correct and that the clockwork is still running there. As we see, they're diligent in their studies. And this one here, you see there's a little thing on the ground. Where is it? Yeah, it's hard to see, but right here, there's a little crossbar and a little white part there. That's another live digital radiation sensor. I'm low on battery. Let me get my other battery. And a little rain gauge. We see here, this again is a snow rain sensor, just a typical, like a bucket, like the old style one, but with a digital counter when the cup fills up and tips over. And yeah, I think that is it for the tour of the instruments. I'm going to, what time have we got here? 10 till. I'm going to take a little break here. Steve, do you want to take over and hang out for like 5 minutes here. I'm just going to see if I can use the bathroom and be back. Feel free to like look through the diagrams or anything. Is that okay?
Yeah, sure.
Okay, I'll be back. There's actually a little chat. There's an overlay for this situation. This is Dan will be back.
Ah, yeah, okay, cool. So I think Peru Mapper asked a question, actually, which I can probably answer. So the results are actually going to be live in a minute. So the Radiosonde's going up and transmitting its data continuously as it goes up, and that's being collected. And at the end of a sort of a suitable period, the data's collected together and turned into a skew chart, which we'll see at around about 6. So that's 1800 UTC. So that's in about 10 minutes. So that'll be very interesting to see the live data from this particular flight. What I don't know is whether the flight is on the high altitude tracker, which we've got a tracker which receives radiosondes from all over the world, and it may be that this flight is actually on there somewhere. So that would be interesting to see. I'll see if I can bring that up now. Oops. So let's see if we can zoom in on where Dan is. And we will look for radiosondes. Just radiosondes. I'm guessing that somebody's made a change on here, and I've not noticed it before. So yeah, I can't find the radiosondes on there. So let's close that down. Right. Has anyone got any other questions you want to throw in? I might know the answer, I might not.
Hey, Steve, how are things going?
Yeah, no problem at all. We just had I just tried to get up the tracker to see if I could find that particular radiosonde on there, but I failed miserably at doing that. So I'm not sure if it's I think something's changed, and it's where they used to be is they're not there anymore. So we'll see.
Which tracker?
On the HabHab tracker, yeah. So a lot of the radiosondes used to show up on there, but I don't know if they've been removed because I can't see any on there at the moment. So you had to.
I looked with Tomasz last night, and there's not enough receivers for this station.
Right.
Commonly received, though sometimes apparently in the past, Mark Jacobs looked back into the records and saw that across the border in Bulgaria, some of the amateur receivers of weather balloons, the network receiver, they have received these flights. Once they pass about 10 kilometers, they can receive it in Bulgaria across the border. And those guys have actually recovered a few, apparently, have come up here and recovered some, which would be great fun. I want to get a hold of them to see if we can coordinate going out to get one of these. As this brand of sonde is from the company Meteomodem, and these are different from any of the sondes that I have seen used in the United States. Oh, by the way, Adirondacks for me asks Steve where he is. Where exactly in the UK are you, Steve?
Coast. Actually, it's about 400 yards to the sea, so not far at all.
Oh, nice. In the southeast?
Yeah, it's in the bulge that sort of is at the rump of the UK. So it's in the middle of that bulge, really. It's
nice.
about 80 miles north of London.
Okay, yeah, that's recognizable. So have you ever actually played with a Meteomodem radiosonde?
No. Just really the IMET ones, the GRAW ones, and Versilla ones. Those are the only that I've played with, really.
Mm-hmm.
Yeah, I am. I am a radio ham, unfortunately, or fortunately, whichever way you look at it. Yeah, G8KHW is my call sign. So a very old radio ham from the 1970s, I think, is when I got my license. Hi.
Yeah, that's my Uncle Russ.
Oh, right. Okay.
He's up in northern New York State in the mountains there. So.
Sounds right. Yeah.
Yeah, these radiosondes are interesting layout compared to the Vaisala ones and the IMET ones that I've seen. Those brands that Steve and I have used are kind of a vertical box with the instruments kind of tipped off the side. But the Meteomodem is like a hamburger with the instruments sticking out from the side. Obviously, it works fine, but just interesting how different the configuration can be of these various sondes. And by the way, the actual measurements that come from radiosondes are temperature of the air, humidity of the air, wind direction and speed. By the way, wind direction, there's no sensor for that on board. There's no little cups and no vane to direct. It actually uses the position of the balloon itself over the Earth. It's assumed that the wind will blow the balloon at the same speed as the wind is blowing and in the same direction that the wind is blowing. So you just use the balloon speed over the ground and its direction to compute the wind speed. And that's always been the way that it's been done with radiosondes. So sometimes they have a pressure sensor in there, but it's not strictly necessary to sense pressure on the flight because it is usually very, very okay to assume that the pressure of the air gets lower as you're higher from the ground. And we know at what altitude it should be, how much lower it should be. Even though air pressure changes from time to time, as long as you measure the altitude, the pressure at this altitude, you just slide that along the chart to see the curve of pressure as you go up, and that will tell you how much to adjust how much to predict this GPS altitude means in air pressure, what pressure level this particular number of feet above ground would be based on your zeroing of the pressure reading.
I think a lot of the modern radiosondes, in fact, have done away with the pressure sensor altogether. They find it more accurate to calculate the pressure from the ground readings taken from the release station. Plus, I think they measure air humidity and temperature, and then they calculate an altitude based on on that, so that they calculate a pressure based on those three things, and the altitude from the GPS, and they find that more accurate than in general than an ordinary calibrated sort of pressure sensor.
That's fascinating. It's hard to make a small pressure sensor that's accurate across a wide range. It's really technically difficult. So that makes sense.
Yeah. So I've noticed that a number of I think there's a variant of the RS41 now, which is like the mainstay, I think, Radiosonde. That they've got a variant that doesn't have a pressure sensor in it, and that's typically what's used. But yeah, it seems strange, doesn't it? But the pressure readings that you'll see have been calculated by using the release pressure and the altitude.
Yeah, it would seem almost counterintuitive that not measuring is more accurate. Not making a direct measurement is more accurate than measuring it and relying on the direct measurement. But that's the special case of not being able to carry the best instrument in the field, in the sky. So we're getting towards the time that we might see the sounding data. But in the meantime, I'd love to tell you about this meteorological station and the hydrometeorological program here in Serbia, its history and what it's doing these days. So the first radiosonde measurements in Serbia were initiated in 1954, and regular radiosonde measurements at midnight and noon UTC had been performed since the 1st of April 1957, initially at the site of Belgrade, Zeleno Brdo. Not sure if I pronounced that right. In April 1987, the measurement site changed, and ever since then, radiosonde measurements have been regularly performed at the site of Belgrade, Kostunjak, at least twice per day. There was a period when extraordinary aerologic measurements were performed at the site of Kruševac, while since the 1st of April 2016, regular radiosonde measurements have been introduced at the new site of Niš Meteorological Observatory, right here, using the state-of-the-art automatic radiosonde robotized system, the Meteomodem Robotsonde. And that's what we got to see tonight. Radiosonding represents a standardized method of aerologic measurements and meteorological data processing, based on the launching of a radiosonde using special meteorological balloons filled with either hydrogen or helium. This method measures, in a standard procedure, air temperature and humidity, atmospheric pressure, and wind speed and direction from the ground surface to the upper atmospheric layers. Measurements of these parameters are performed up to the atmospheric level to which a balloon carrying a radiosonde rises before it bursts, most commonly attaining the height of 30 to 35 kilometers, depending on the characteristics of the balloon and atmospheric conditions. Measurements at various heights and processing of relevant meteorological parameters are performed in line with the recommendations and procedures of the World Meteorological Organization. My battery's getting low, hold on. Come on. I'll reconnect Steve if this dies. The WMO is the international organization that collects data from all countries' balloons and ground sensors and satellites and commercial aircraft, temperature sensors, and dumps it all into a common database for any country to pull for their analysis. So basically, it's one of the wonderful scientific equality sharing cross-border activities where everybody shares weather data in a very friendly manner. It's a wonderful community of weather science worldwide. So a radiosonde is an instrument designed to be carried through the atmosphere by a meteorological balloon equipped with sensors and with a radio transmitter that transmits all the information down to the ground. The position and wind speed are measured by GPS. So that's information from the Hydrometeorological Department's webpage, which I will see if I can show here. Steve, thank you. You're on top of it. So this webpage you can go to, you can see, we'll post the URL in the description after the video airs. The lovely description we just read about there. And there's also the blue links at the top. Boy, it's dark here. The blue links at the top show you the latest graph of the balloon's collected data after it's analyzed and calibrated in a chart that shows you the conditions of the atmosphere from ground until the top of the sounding, presumably when the balloon bursts, I think is where the chart will end, but it might end somewhere below that. So we've got a question in chat from Adirondacks for me. Is this the first weather balloon location you've come across in your travels? The crickets have woke up. I forgot you might hear the crickets. They are loud. Yeah, this is the first weather balloon I have come across randomly. Yeah, and in fact, this is the first time I've been at an official government weather balloon station that's active. I've always meant to go to one in the US, but never have gotten around to it. So it's really exciting. The people here have been wonderful to welcome me and trade stories about science and measurements and instrumentation, about both of my experiences in ballooning and their weather studies, their academics, and their technical work here. So do we have an updated sounding product yet, Steve? A Skew-t chart, I mean. I have to relocate to under the street light here in a minute. You're not going to be able to see me. So the Skew-t chart, I will show you one before it gets too dark to show you one, although it's probably already too dark. Type of chart that is produced from the sounding. Oh yeah, we can see it. Right side up, how about that? So you can see we have black lines that zigzag up and down this paper. And there's a lot of information on this chart, a lot. So much so that I can't explain it all to you tonight. I honestly ran out of time to remember to re-look up all the details. It's so much dense information, but we'll look at some of it on here. I'm not going to point it out to you all here on this paper because it's probably too low res and it's dark, but just generally show you a couple things. Along the left edge here, this is altitude. And it starts at ground level here. This is where the balloon took off, and it goes on up by pressure. It's not by feet, it's by atmospheric pressure. We talked about how they measure the pressure level as it climbs. Well, that's actually how they refer to the data. They don't reference feet for this measurement. They reference how many millibars or pascals, etc., of atmospheric pressure that was the altitude where that measurement was taken in pressure. So, for example, down at the bottom here is 1,000 millibars, which is basically sea level pressure. And it's hard to hold this when it's backwards. And this station, you can see, started not at the bottom. It started at, this is a log chart, which is always hard for me to read off the bat. So the lines here we have are 1,000 and 950. So it's pretty close to linear. So this was about about 970 millibars. So that's basically the absolute pressure of this station today. So if we looked up the standard atmosphere chart, which converts feet to pressure number, that would show us that we are something like 1,500 feet above sea level, I think, here. Something like that. And so that's why the chart starts not at the bottom. If we were at the ocean side, like a beach side station, it would start basically at the bottom of the chart. And mountain stations, you know, their black lines would start somewhere around there. So pressure goes up here, and you see there's a lot of crossing lines. There's a curve and diagonal lines. There's lines going this way, lines going, going that. I gotta look. There's lines going that way, and lines going this way. And over here on this side, we see these little flags. See those? Like little golf clubs? Those are what are called wind barbs, and they illustrate at each of these altitudes, you know, at this pressure, this is a wind reading. It tells you what direction the wind is going in and how fast it is. So, for example, we can see, it's pretty standard. This is probably blurry, but you'll get the idea. You can see here, this one is pointed straight left, and it's got one little golf club hook on the end of it. And pointing straight left means the wind is blowing to the west. I think to the west, probably from the west. Yeah, sorry, I can't remember whether it's from or to. And each of the barbs that stick out, basically the little hooks, you can see there are more on this one and even more on that one. Or on the stream, it may just look like the little hook is thicker, but there's one barb, two barbs, three barbs. And each of those are an increment of wind speed. Steve, do you remember how much the wind barbs represent? It's not that important. But
No. Sorry.
yeah, I don't either. But you can look it up. You can Google it, everybody, if you want. And there's a very cool reading here that I didn't see earlier today. There's two things. There's a red dot with a line there. That means ground level. And then another red dot up here. These are special altitudes. I tried to zoom by stretching. That's nice. What this says here is, I think the light is getting ridiculous. It says tropo, 9540 meters. And what that indicates is, that's here. Look what's over here. Oops, here. There's a big chevron. Sorry. There's a big chevron here that turns around. It's this turnaround. This turnaround, what that means is this line is temperature. Just by seeing this, the shape of this, we know that's temperature, because the temperature in the atmosphere, in the troposphere down here, goes down as you climb in altitude. And in the stratosphere, it goes up as you climb in altitude. And the boundary between troposphere and stratosphere is not a fixed altitude. We don't say it's 45,000 feet, but though it may be, it fluctuates. It might be 45 on one day, it might be 40 on another. But it's this is the boundary called the tropopause of the top of the troposphere and the bottom of the stratosphere. I have to say, I'm very impressed with the light levels on this iPhone. I can't hardly read this, but the iPhone picks it up fine. And so we see there's numbers here on the bottom. These represent temperature. And they range between about plus 50 here and about negative 50 C over here. And so we see, where's zero on this chart? Well, this chart only goes to -30. So the chart may be, scale may be adjusted per, the data's range, which would make sense. So here, it looks like the temperature at ground level, we see 20 C, 30 C. So temperatures, it's a tricky bit. Temperature is not a straight line. Temperature is these diagonal lines. One of the little puzzlers of this chart. So we see, so to read the temperature, you can't just find a point and go straight down. You need to find a point and then go diagonally down. So we see this, the dark orange line it's on. We follow it down. It says 20 C, but then we go a little to the right of 20, and we see that it's about 1 degree to the right. So 21 C was the temperature here on the ground. When we saw that balloon come out, that's what it measured. The first thing it measured was 20 C. Well, sorry, this is not the graph from tonight. This is the graph from this morning, from this afternoon. This is the noontime graph, and we're waiting for the 6 p.m. graph to be available for download. So this was today from a balloon here, but not this one. Hey, Steve, did we get it? Yeah, it looks like, I can't see the time factor on it, but I'm betting that's the one that Steve brought up for, that's today's. I'm going to relocate so the street light lights me a little bit, because otherwise I think we're getting to ridiculous light levels. So we see here, the soundings. Let me just move my tripod while you're scrolling that, Steve. So this street light might help a little. Oh yeah, that's a little better. Okay, so yeah. So can you zoom that wide, Steve, down at the bottom? There we go. Oh, look at that. So you see something similar to what we were just looking at, where the, do you want to, sorry, I can't control a cursor here. Steve, can you point out the bottom of the dark black zigzag line there? There we go. So to read the temperature at the ground level point, the bottom of that line, we look at the diagonal lines, and we see that it's just to the left of 20. And you can see now on the computer, there are faint lines in between the big ones. And each of those are a single degree. So if we look over, it is 2 degrees. The little hook there ends after one thin line and on another thin line. So that is 20 minus 2, that would be 18 degrees C. It was 21 at noon and 18 at 6 p.m. The day got cooler, which made sense. What are those for American units? What is 21 C in Fahrenheit? It is 69.8, it's 70 degrees at noon. And what is 18 degrees C in Fahrenheit?
It's 64.4 degrees Fahrenheit.
So it's 65 Fahrenheit when the balloon launched. A little chilly. I'd say it's colder than that now. I'm getting a little chilled. So we see there's the black line is temperature. We just learned how to read the temperature of that. And next to that, we see the dotted line, and that would be humidity, which is the other sensor that the radiosonde carries and transmits measurements of. So the humidity is measured, I think that's humidity. Yeah, scroll, Steve. See if there's labels up at the top. Wait, was I reading those wrong? These are complicated. Is humidity the green lines? Let me, anyway, I'm pretty sure it's lines that are going, it's not the lines that are temperature. Wait a minute. Was I reading this really wrong? My weather friends here are probably shaking the screen right now. Scroll back up to the top, Steve. We see... Oh, yeah. I don't understand why there's...
Is that dotted line dew point, Dan?
No, oh, maybe.
This one, the one that sort of looks like temperature, but
Maybe. I really shouldn't research that. Let me just Google for a second. I don't want to miseducate.
yeah. I don't know what the green lines are. They're quite different.
There's something in the earlier one that I do want to look at that is missing from this one. That's kind of exciting, but we'll get to that in a minute. You're right, Steve. It's dew point. Totally dew point. There's no humidity on this chart because really humidity is not so helpful for day-to-day weather analysis, predictions. Dew point is what really matters for our world interactions with weather, because the closer dew point is to temperature, the closer that dotted line gets to the black line, the more the relative humidity is higher. So if that dew point ever gets to or almost touching the black line, that means it's 100% humidity, and there will be clouds and fog, depending on the altitude it's at, and possibly, depending on the temperature profile, possibly rain, precipitation. And in fact, these charts, the computer will be able to tell when when the dew point is close and when there's a temperature condition that might indicate precipitation. Steve, can you bring up the one from earlier today, the 12 o'clock? I think that was in the download folder.
Okay, hang on.
And the reason why I want to show you guys this is because, look at that. We had thunderstorms today. Look at that red little section there where the dew point comes near the temperature. And let's zoom right in on that. Yeah. So the dew point comes near temperature for a little while. For an altitude, we can see the altitude of 750 millibars at the bottom of that red section to 625 millibars on the top end of that red section. What altitudes are those?
So it says about, it's on the right-hand side, Dan.
Oh, perfect. So 4 to 2.5 to 4 kilometers.
Yeah.
Is that's a cloud deck, almost certainly a cloud deck, and probably has some potential for raining. And that will also be indicated by some data up on the top corner of the Skew-t plot. There will be a convective index that we'll look at. It should say CAPE or CAP. Yeah. So that's interesting. Again, I apologize. I'm not completely up to date on this stuff, but I will release a video that corrects any errors I've got here. But this is kind of fun to do in real time. You see here, we'll compare the CAPE on this chart to the CAPE on the chart from the balloon we just saw. So this one says, I was right, or close to it. So this is the balloon we saw tonight at 6 p.m. UTC that we saw just an hour ago or so. We see the CAPE number at the top left there of the screen. Can you circle your mouse around it, the black text in the key box, little below that? It says CAPE.
Yeah.
Yep. So that says 0 joules per kilogram. And that's just by the unit, that's probably heat energy per kilogram of air. And if we switch to the one from midday today, we'll see that's 30 joules per kilogram, which means there's instability in the atmosphere, which means you have the potential for a storm. And indeed, that red shows that we had clouds and likely potential for rain. If we scroll down on this plot, this is the plot that shows us the red section. And that's kind of neat to see. So let's go back to our tonight's plot. And based on, Steve, what you realized, which was the dotted line is dew point. If we scroll all the way down to the starting level at the bottom, we can figure out which of these lines is.
Oh. Haha. I think we might have lost Dan for a bit. Probably run out of batteries. Yeah, these charts are beyond me, really. I mean, I've seen them before, but I couldn't really add anything to what Dan's telling you. Quite interesting to see how high it went, actually. So, chart ends probably at about 16.5 kilometers. So, certainly would have thought burst would have occurred a lot higher than that. Okay, I think Dan's come back. Here we go.
That was funny.
Dan.
Can you hear me?
Yeah.
Great. Sorry, I'm back. Sorry, my data plan needed a manual kick to roll over to the next block I bought. It costs about $10 to do these live streams and data here, which isn't bad. We push about 4 gigabytes through like a 2-hour live stream. So that's pretty good for mobile data, prepaid. So we see here that the dotted line on the left-hand edge of these two lines here, we can determine which of these cross-hatched lines or the green swoopy ones, which of those refers to the measurement of dew point. Because we can see that the dew point was spread from the temperature, and we know temperature around 20 C is correct. I can verify, 20 C is room temperature. Wasn't far from that. So we know the 20 C number there is correct. However, is that referencing the green swoopy lines or the orange ones? Oh, that's tough to tell.
Mm-hmm.
Well, the dew point. Okay.
The temperature.
The dew point would not be below 0 C here. Go ahead, Steve.
Well, I was going to say, there's some form of temperature because they cross the temperature lines at 1,000 millibars. So,
yeah.
But
scroll up to see if there's a reading at the top of the green swoopy lines.
Is there? Okay.
Let's see if there is at the top of the document.
No.
Beautiful, clear night here after a stormy day. And the sky looks beautiful in the picture.
You can see that the green lines sort of go, along the temperature lines.
Can you scroll to the top?
Yeah, that's it. That's as far up as it goes, Dan.
Oh, I think I've lost the live. Let me reload here. Really? Again? Did you do this again? Okay. I think maybe I'm back. Am I back?
Yeah, you're there. You've never dropped out, Dan.
Okay. Yeah. Sorry. Yeah. My screen hadn't updated when you scrolled, so I apologize. So yeah, we don't see any markings on the green, but we do see that the horizontal curved, the curved orange lines here appear to have temperatures on them. So I don't know which is which, but we'll come back to that another time, another stream. But you can see here how this will show you at a glance to a meteorologist what altitude a cloud might be formed. For example, here we might see clouds forming in that area around 600 to 650 millibars, which is 3.5 to 4.2 kilometers. So they're close, so they might have some formation. One of the reasons why the earlier one today was red, if we can flip back to that, I think you see there's a very sharp hook at the top of the red in the temperature line, where the black line curves sharply over. That is a temperature inversion, and that is a classic feature of an unstable atmosphere that you see with raininess or storminess. And that's probably what triggered the computer to assign that little red shaded area to that section there.
On pico balloons, we often see them slowing down, at that layer. Or I've actually physically seen one when I followed it in my car, bumping
Yeah,
on.
we downloaded it. We're looking at it now.
Last time, if you have USB, I give you.
Oh, I actually have it now. We download it. I did off the web. Thank you. We're looking at that now. Thank you. The meteorologist here just let me know, alerted me that in case we hadn't found it yet, that the latest Skew-t immogram was available, which was really nice of him. These are really, really good guys here. So, yeah, did we have any questions, Steve?
Let me just check. Not since the last lot. It's just a chat on. No, it's pretty much the same as no, nothing new.
Okay.
So I was saying, Dan, I think I've seen pico balloons bump along under this inversion layer. I followed one in my car for quite some miles, and it just didn't want to go up. It just sort of like stayed there, and I presumed it was the inversion layer it was bumping under. And you see the temperature go the other way. Instead of going down with altitude, it actually gets warmer at that layer.
Yeah. Let's switch to the current immogram, the current Skew-t.
There you go.
So if we scroll to the so that you see we don't have any of those sharp hooks in this chart, and we don't have any red band. And that's because this guy is, as you see, almost completely clear. Though, I wonder if we can catch this. You can see there are clouds up there, but are very thin. Like you can see down by the horizon. Oops. You can see there's. Oh, thank you, Steve. You can see there's obviously a cloud here, and there we go. Okay, I have to applaud Apple for this camera. My gosh. We can see that there are some very thin clouds, and you know what? I'll bet those are at 600 millibars at 4 kilometers, like we saw from that chart. Like we just discovered these clouds mathematically from that balloon flight, and that's what these radiosondes are all about. Is the computer now does that interpretation, but it's totally possible for you as an individual and as a weather person to take a quick peek at this and see, dew point comes to temperature, that's going to be a cloud. And that's really important if you need to do like experiments or you need to predict the weather. Like sometimes, you need faster weather predictions than the international weather models will produce. Like weather prediction models are huge, and they don't run every minute. You can't say, all right, now what's the weather gonna be? They take so long to run, and they get data in big waves. balloons. Like they collect data from worldwide, like in a wave, like 4 times a day or twice a day. They get all the balloons from the world and all the temperatures, all the humidities every 6 hours or so, or sometimes every 4 hours. And then they run the whole prediction algorithm, which takes supercomputers. Then it spits out like every 4 hours or every 6 hours a prediction. So it will be 6 hours between the time you had an estimate of the weather to the time you get an update on that estimate. But if you launch a balloon, like if you're doing a rocket, if you need to launch your rocket 3 hours between or 5 hours after the last sounding, the data could be unreliable in the extreme, particularly in places like Florida, where there's a lot of unstable thermal activity. And so you can send up your own radiosonde. In fact, you guys out there, you can buy radiosondes. Intermet.com, I know an American company sells them to any scientist. And I think Vaisala is harder to buy single ones from, but lots of companies. You can launch one, and there's free software out there on the internet to dump all the text, the temperature measurements and the humidity and the GPS file that you'll get from a radiosonde received flight. You can dump that into this software, and this Skew-t chart that we've been seeing will just magically come out. And you're waiting for your rocket launch, and you want to see, okay, there's a cloud. You see clouds. There's one back there. Clouds are fine, but not if the clouds are going to make rain or hail. Like if that's your requirement, you can find out. You send a balloon through that cloud, you'll get an actual reading you can see. You'll get that little red part if it's unstable. And it's just so cool to me that this is like real-time interactive exploration of the atmosphere that makes sense, that you can actually get useful action out of.
Yeah, I've got a couple of UK rocket companies now that are buying balloons off me for before they want to launch, they launch a balloon.
That's fantastic. That's really cool. Do you have you referred them to Radiosonde companies, or did they?
Yeah, well, When they first got interested in doing it, they contacted me and we sort of exchanged a few ideas. I don't know which one they're actually using, but I think the GRAW system seems to be the most reasonable. I think in terms of like the cost per sonde and base station. The little base station's very, very dinky, little receiving station. I don't know about the IMET ones. I imagine that's an open protocol. I think IMET they actually specify the protocol so you can make your own receiver if you wanted to.
I think that's one of the reasons. I think that's one of their selling points, is that their protocol's open to get a little more market share, where their sondes, the IMET sondes, are made a little simpler and more basic, at least for the old ones, the IMET ones. Their new one seems to be similar to the Vaisala in build style, but it is really nice for amateurs and for some scientists to be able to not have to use the radio you buy from the manufacturer as your only way to receive data. Because like the radios from Vaisala are unbelievably expensive. I worked for a balloon project that looked at buying one, and I quoting expensive equipment is kind of a black art, and I know salespeople have different quotes for different people, but I will say it was many, 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 many thousands of dollars for the receiving system for the Vaisala radiosondes. And the radiosondes were $30-$40 or something. It's something under $100. But the system, like the number of times we had to fly radiosondes, would equate to like 200 a year. It did not make it worth it to buy the system, particularly just as we were experimenting. But the IMET ones, the sondes were $100, but the ground station was $1,500, and for all of our data actual receiving, I ran a software-defined radio, an RTL SDR USB dongle, into the open source NOAA software that's available online to decode the IMET sondes. And so for $30 for the USB dongle and free software, I had a working system, and the antennas for reasonable balloon ranges aren't too bad. Like a typical sonde will go not more than 100 kilometers, would you say? Do you think, Steve?
Yeah,
like
it's difficult to say. It really does depend on the wind, but yeah, most days it's probably less than 100 kilometers.
And that doesn't require a high gain pointed antenna. You can just rely on a little stick on top of your roof. But that's where, if you have special scientific needs, like if you need one to go far on a balloon that climbs very slow, the built-in systems from these manufacturers are often not going to cut it, or going to be hard to deal with. So anyway, that's where an open protocol makes it more flexible and nice to deal with. But I'm getting cold out here. It's getting very damp, so I think I'm about ready to wrap the stream up, though I've not gotten to showing the instruments that we wanted to show from inside these boxes in detail. Let's just take I think the one I would like to show them, Steve, before we go is the Psychrometer and thermometer that is inside of one of the screened enclosures that we saw here. We can see the these little beekeeping houses. This one right here. Sorry. this thing here is the other enclosure.
Which one of those is it? Which one of these devices is it, Dan?
It should be the Psychrometer.
Psychrometer doesn't seem to be in the list.
Just look for the one with all the thermometers.
Ah, okay. I found that. I think. Let me flip that on. Is that the one?
Beautiful. That's the one. Excellent. So let's go a page ahead there. Yeah. Keep going. A little farther. Yes, let's zoom into that color picture there. I'm going to grab a bottle of water. And it is officially dark here. So let's go up to the picture above that. Yeah, let's zoom right into the ones on the bottom, those two glass tubes. Yeah, right in there. So this setup, there are two glass tube thermometers like this inside this that Stevenson screen, the white bee house on stilts. Actually, can you zoom in a little more even? Yeah. Okay, so what you see here are two thermometers, and the meteorologist and technician here showed me these inside the box and explained them. Like, it took a while to explain how these work. They're not just thermometers. These measure and record the daily maximum temperature and the daily minimum temperature. One uses mercury and the other uses alcohol. And Steve, if you can zoom into the left-hand bulb ends of these, you'll see they aren't both the same. They're not like, you see one has a fork. I don't know, can you zoom in any more, Steve? Actually, let's turn the chat off for a minute. I'll do the chat. There you go.
That's as much as I can zoom in. Sorry.
Okay, that's fine. I think our picture is not that high res anyway. So you see one has a fork and the other has has a little ball on the end there. The top, there you go. The top one is mercury, and the bottom one is alcohol. Now the top one with mercury, I have to make sure I remember how this works. Minimum. Yeah, mercury is the maximum thermometer, and the alcohol is the minimum thermometer. The way the mercury works is it's got, we'll look through the documentation just to verify my assertion here, just in case, but the mercury has a little one-way valve with a vent just after the bulb. You see where it's clear between the bulb and the white ruler section on the left? It's a little one-way valve.
Okay.
So that as the mercury goes up that tube, when it gets to the highest temperature in the day, and then starts falling again, the mercury up in the ruler part of the tube is left where it's sat, because there's a little air gap here, so that when the mercury retracts in the bulb, it just sucks air in instead of pulling the mercury with a vacuum back into the bulb. So you're left with the temperature, the mercury in that horizontal tube, the top of it stays at the hottest point, hottest reading of the day. Isn't that wild? So the alcohol one is even more complicated. By the way, it was beautiful. They showed me these up close, and the precision and the engineering and the tiny little components is really amazing in these glass instruments. And they're sufficiently precise enough still today. It's wonderful. So the alcohol one has, it's just a regular alcohol thermometer, with the glass tube up through the measurement section. There's no one-way valves in it, but what it has, the picture's not good enough to see the thing. There's a little black, there's actually a little rod of metal in the glass tube. Oh yeah, that might be it, Steve.
Yeah.
My thing is small. Yeah. So it's like a little rod, and it's got basically little bumps in the ends to keep the rod centered in the glass tube. And the way this works is I believe you shake the rod down to the maximum temperature, the current temperature of the alcohol. You shake it so that the rod goes all the way to the tip of the alcohol for the current temperature, the meniscus of the fluid. And the surface tension of the alcohol keeps the rod from protruding out into the open tube above that. So it gets stuck on the meniscus, or stopped by the meniscus. And as the temperature falls through the night, the meniscus drags and pushes the rod down the tube, down colder and colder readings until the coldest point in the night. And then when the temperature rises, the alcohol meniscus pulls away from that rod, and it leaves the rod at the point where it had been dragged lowest down the scale. And so you read these just once per day. The day one you read in the evening after the maximum temperature, and the night one you read in the morning after the minimum temperature overnight. So these are present in this first box here. Now let's scroll down and see if we have the other things I'm looking for in this document. Yeah, keep going. I think keep going. Yeah, it's not this document. See if there's a list, if there's like a humidity or hygrometer document. This is it. Yeah. Okay. Sorry, I misnamed this one. Psychrometers. So that's not the one we have here. That's a portable one. Okay. Yeah. Here we go. So if we zoom into these pictures here, this is a beautiful set, a double set. So we have what appear to be a normal set. They're both thermometers that measure temperature normally. They're both, I believe, mercury bulb thermometers. And what you see here, this is a very standard instrument. Not much special about it, other than they have it here. It's interesting to have a manual version. Steve, can you zoom in any further? I apologize to keep asking for this. There we go. Yeah, let's look at the bottom end of the instrument. Beautiful, beautiful view. Okay, so you see there's a little silver cup, and in that cup is water. And water or alcohol? No, water, of course, water. And actually, I can't remember. Anyway, it's water or alcohol that evaporates. No, it would have to be water, because what you're trying to measure is how cold does something get when water has evaporated off of it until humidity prevents any further evaporation. So what you see, the little white string coming up out of the cup, is it goes to a little sock on the mercury bulb. And it's fabric. The string is fabric and the sock is fabric. And that keeps the bulb wet. Whereas the other mercury bulb on the bottom of the other glass thermometer is just in the open air. And this is the classic psychrometer. This is a device to measure dew point. You have what is called a dry bulb, which is the bare thermometer on the left, and you have a wet bulb, which is the one with the sock on the mercury bulb on the right. And when you have to blow air forcefully at speed across these to make sure that water evaporates quickly, and you will see that the wet bulb temperature will drop lower than ambient, than the right one is. And it will slowly stop dropping. And using some math, you can tell what the relative humidity is from these things. And I believe, this is reaching in my memory, Steve, is the wet bulb the dew point?
I think you're right. I think it is, yeah.
Yeah, I think that's the dew point. So this whole thing is a method to calculate humidity, relative humidity in the air, and dew point. And if you scroll to the right picture, same level, you see a clock-wound, key-wound fan that blows air forcefully against the wet bulb. Now, they have the same device, but it's got an electric motor on it. But it looks the same, just with a cord going into it. So
a clockwork fan, yeah, that's cool.
Yeah. Well, that's. I think we'll wrap it up with that, Steve.
Okay.
Both on screen here.
Just see if there's any other chat.
Yeah.
Not really.
Okay.
Yeah.
Well,
watch out for wild animals.
Yeah. Well, you can turn the chat off there. Oh,
okay.
Yeah, nice. So let's see here. Just about done. So I want to thank you all for watching this afternoon tonight. This has been fun for me to give a tour of. These recordings will remain online. And I'm actually going to be coming out at the same time tomorrow night to watch the next one and talk a little bit more about this stuff. And I want to say this stuff is made possible here with contributions from several people on Patreon. I really want to recognize those people: Mike Bowen, Sheila Bunch, Ben Lathan, Ken Howard, Sophie Searcy, M. Fong, Ashley Meyer, Robert Quattlebaum, and Steve Randall. Thank you, Steve. And please consider contributing so that I can continue to bring content like this and other educational info out to the world for balloon science and now some weather science too. Go to patreon.com/balloonscience and consider donating today. I'd really appreciate it. And thank you all for showing up. Take care.